Good evening, everyone. Can you hear me? Okay. Good evening, everyone. Welcome to now. Before we move forward, I would like to briefly introduce my organizer for the last 3 sessions. The third one we are doing. So Professor Jutta Ludwig-Müller is organizer of the first session was 2021. That was in March. And another session in March. Both of them were purely online, and this time the participant requested that we should have 2 years difference and also to have it hybrid. So welcome, Jutta.
Thank you. Yeah, welcome everybody to this. Fidele pointed out our third workshop now together, and since we have a lot of participants, I really hope that you enjoy it, and hope to be also sharing that session together with you, Fidele. And also for the rest of the workshop, there are a lot of hands-on sessions. Everything that people enjoyed the previous workshops, and I'm happy that we can continue.
So for those of you who are joining for the first time, maybe I say briefly the story behind this workshop. I don't have any slides here. From 2020 to 2021, I was enjoying a guest lectureship at the Technical University in Dresden, where I was hosted by Jutta. And so during this time, we had option to do a couple of things. And one of them, we were considering to develop a mobile phone app to study natural product chemistry. But it was important to develop something computational and natural products. And then the idea of having a workshop, online workshop, particularly at the time when there was Corona. And the idea was welcome, and we had a lot of enthusiasm. At that time, Kiran was there, and Kiran also played a very important role in setting up all the organization for registration of participants. And the first year was quite a success. Actually, we had speakers and participants from all the 5 continents, and it was so nicely done. And at the end, we had the report of this workshop was published in Journal of Chemoinformatics. And the next year, of course, there was a lot of enthusiasm. Of course, we know the next year, Corona was slowly getting out, and many people were getting bored with many online meetings. So we decided to do it every other year. That's how we moved from 2022 to 2024. And then in 2024, we have the opportunity to now have it hybrid. So some people are actually attending in a physical location, because that was the idea that was discussed that was suggested by the participants at that time. Again, in 2021, we had many speakers and participants from this time in all the 5 continents, and more than 150 registrations. And so we are very excited, because we see that this is a platform where a lot of students, master students, PhD students, and postdocs can benefit from the experience and expertise that our dedicated speakers bring to us. So I am very happy that we can start this year. On this note, I would say a couple of things about practical things about the workshop. The first thing is that we are following Central European time, because I got a lot of emails this morning, and like, are we starting already? We are following Central European time. So those of you who are in West Africa, this is West African time. Those of you who are in East Africa, Kenya, Tanzania, you are 2 hours ahead of us. So those of you who are in the United States, you have different time zones. So bear in mind that we are following Central European time. So we are sorry sometimes our talks may be in the middle of the night for you or early in the morning for you. We beg your indulgence for this. The second thing we are going to say is that there are going to be not many hands-on sessions at the same time. The first year we had 5 hands-on sessions running at the same time. And from that year, we decided to do 4 hands-on sessions, but in 2 days. That means that every day there are going to be parallel hands-on sessions. Yeah, we had a lot of complaints from previous participants that they would have loved to have attend each of the hands-on sessions. So what we did this year is that we have for day one, 2 hands-on sessions that are running parallel, and day two hands-on sessions that run parallel. Each of them is 90 minutes. So we have carefully divided the hands-on sessions two. We have bioinformatics and chemoinformatics. So if you are more interested in bioinformatics, might want to look at a workshop on Galaxy or something like that. And if you are more interested in chemoinformatics, you might look for a workshop in drug discovery, molecular docking, and things like this. So in essence, you will choose your workshop depending on what your interest. So we have shared the book of abstracts, and then we have for day one hands-on session for chemoinformatics, one hands-on session for bioinformatics. Then day two, we have the same. This is the second important information that I would say. The third very important information is that we delayed the registration this year, the deadline for registration, because we were having a lot of technical difficulty, particularly since we are running hybrid for the first time. We want to be very sure that we don't miss out on anybody, and we are hoping that the next year will improve. That is basically it. And the last of the important announcements is that at the end of the workshop, we are going to complete the survey, and that when using the survey, you can request for a certificate, and you are going to get it delivered to you. So that's how we have functioned in previous years. So before I allow my co-chair to introduce the first speaker, we still have about 8 minutes to go for the first speaker. So please, if you have any questions, just raise your hand and we will direct you to ask your questions before we start. So Kiran, thank you very much for putting all this together. I'm so glad that everything is working well.
Thank you. So this time I would say, most of the, as I said, the KMS Foundation, the members of those people are doing, and actually it's a good progress for me, or let's say our foundation. It's last time I was doing more or less. This time others are actually, that's a bit for myself.
All right. Thank you very much. Unfortunately, this time around, Kiran is not going to keep the first 2 sessions. Then behind the scenes putting things in order. Yeah, please, if you have any questions before my teacher introduces the first speaker of this workshop, please raise your hands and allow me to ask your question. More practical things, and we still have 7 minutes. And we also say that for the first time we are recording the workshop, so that those who have inconvenience in the time zones can always follow later on, because this is some of the complaints we had last years. We have advertised this year in LinkedIn, so, and also the platform, social media platforms. So we are taking your feedback into consideration. So that's why we have the survey at the end of the meeting. Yeah, I cannot see any hands on. So
there's the possibility of people asking questions. You can always use that today. And also there is a possibility of asking polls. You can make polls.
Yeah. So which means that you can actually raise your hand and tell me how many polls. And next thing is that you can also, if you are not confident, you can write your question on the chat and we can read it. So I would say up to now there are no hands raised. Allow some time more and or maybe I would say a couple of things about myself if you want to know, because I am literally go to participate only in one talk in hands-on session in the breakdown. So some people may never get to know me. My name is Fidele Ntie-Kang. I come from Cameroon, and I work at the University of Boya, where I am heading the Center for Drug Discovery. And before this position, where I work as an associate professor, for this position, I have spent an extensive time in Europe as well. So after my Ph.D., I came to Germany, where I was working with Professor Wolfgang Siebel, the Institute for Pharmacy in University of University in Halle. And after that stay, I have spent some time also in Prague, in the University of Chemistry and Technology, Professor Daniel Spozin. And then I spent 1 year also in Dresden, as I mentioned in my talk. And I have been, beside working at the University of Boya, I've also been a guest professor for 3 years in Nelson Mandela African Institute for Science and Technology in Tanzania, where I directed one PhD student who is one of the speakers in this meeting. And since then, I've been very busy with setting up a Center for Drug Discovery. So I've discontinued most of my positions outside Cameroon. So that's basically who I am. I'm very delighted to organize this workshop, and I hope forward to having you guys enjoy yourself. So I pass over to my co-host, to organizer, to introduce the first speaker of the day.
Okay, well, thank you. Yeah, today's first speaker is Egieyeh, and you may know him because very well-known and respected researcher in M.Sc and also bioinformatics, and he also has a record Europe, locations in Africa, and so I'm a perfect person to have the meeting starting here, and I don't want to take, I mean, we still have some, but I don't want to actually take too much time your talk, and so I would really like to give you more, even though it's only 4, and we all look forward to your presentation.
Thank you. I'm just going to put my video on.
I think you need to share orientation of looking for the whole screen.
Is another page. Are you confirmed you see this slide? Can you see the slide? I think the slide is showing, but it's not full screen. Okay, that will share.
on my side, or was it on your side? What's that on your side?
That's good. Side.
I'm live.
Okay, the full screen of the workshop is right there.
Yeah. Is it outline?
It's just the workshop poster.
Okay, I see there's a line. There's a line. Move on to the outline.
Oh, okay.
You see the outline?
It's still on the same spot. Oh, yeah, it works now. It works now.
Now it's the outline.
Yeah, I think there's some sort of a line. So my slide might be behind my speech. What I noticed. Okay. So good afternoon, this afternoon. I started Jutta. The privilege to be part of this again. And I want to really thank the organizer for giving me this privilege to speak. And I believe somebody's on me. Okay, cool. Yes, the organizers will attend to that. All right, cool. So my job here is to, I believe, set the tone for this workshop. And briefly, in the next couple of minutes, I want to talk about the Menace of Malaria, which is the area that I'm interested in. But it could be anything. It could be, we also know that the AMR, the malaria resistance, become what most people refer to as silent pandemic. And secondly, we delve into the use of natural products, which also is the focus of this workshop of Metabolite is referred to here, and how we can now use computational resources to harness those natural products that we have, especially bias to Africa, permit me, and then I will take a case study to show that these things are possible. And I want to also acknowledge everyone that will speak after, because there are more technical things that we discuss with how these resources are used. Okay, so that's essentially what I'm going to talk about. So I'm going to start my conversation by looking at my presentation. I've changed this disease is very passionate, is very passionate really to me, because all my years growing up I've suffered from malaria, except in the last couple of years that I moved to South Africa. And it has been to say the least, a very traumatic experience for me, to the point that I have to, most of the time, learn to inject myself when there's nobody at home, and I start having rigors and fevers, feelings, and the rest of them. So when I do a PhD, I to look into this, particularly looking at those plants and natural products that eventually were concocted by the mom and under the, of course, instructions and advice of practitioners, and that I use to prevent malaria and also to treat malaria way back then. And that was the focus of my PhD. There's been, of course, if you look at this data from WHO from 2000, year 2000, say about 2002, there has been a decline in the global death rates from malaria. A whole lot of programs has been in place, and I want to applaud everyone that's working tirelessly, including those people on this platform and researchers, to ensure that we have achieved this decline. In the last, from 2022 till now, it has sort of stabilized. Majorly because resources have been diverted slightly towards the pandemic that we had. So some of these infectious diseases were temporarily neglected. But now the gap is over, there more attention being paid to this particular disease, especially in Africa. So even though it's leveling out, we want to see more decline. Now, based on that data, that if you take a snapshot and look at Africa and look at the percentage contribution to global death, you find a very large percentage in the country of Malaria, and of course, so many other countries, Democratic Republic. No matter of fact, all of them account for half of the malaria deaths globally. Nigeria, Democratic Republic, Niger, and Republic of Tanzania. So it's a big concern for. I mean, in terms of all that done so far, we are still at this level. And a very staggering data, very sad for me, the fact that Nigeria accounts for 38%, over 30% of the global malaria rate in children that are under 5. So it's for some of us, it's very sad that we in this age we still at this level. We need to do more to save the life of the future generation. So there's a global strategy that the WHO has put together and to ensure that we sort of get a handle on this issue. If you look at the 3 strategies, strategies, basically look at access to prevention, diagnosis, treatment as part of the universal health coverage, and also to accelerate effort towards elimination. We'll talk more about that in a few minutes in order to achieve that area of history. Some countries have achieved, and also to ramp up what in terms of malaria surveillance, intervention, to also respond to malaria and also to eliminate some communities. There have been various treatments for malaria. I mean, I've practically used all the drugs that you see on my side right now. At one point or the other. So the question now is not that the drugs don't work, but most of the time we are reinvented by the minds of the mosquito. And so we keep on treating, and we all know what that will lead to in terms of resistance. But just to give you a snapshot that there are drugs out there that over the years have been developed for the treatment of malaria. However, like I mentioned, because of a couple of factors which I mentioned, having resistance to this medication. And if you look at the distribution of the resistance that have been noted, you still find a majority of them within Africa, a couple of those outside Thailand and the rest of them in the East, but majority you still have within this particular region. Particularly because of the tropical belts of the world seems to be very, very peculiar and suitable for the mosquito itself. So you see a lot of that resistance coming up within that space. So if we now take a look and see what is actually driving this resistance, the same. There are various factors, and the WHO identified 3 main factors: the parasite factor, the host-related factor, and the environmental factors that are driving it. But without getting into the details, if I look at the host and drug-related factor, which I think is central to this workshop, there are unusual genetic structure within the parasite itself that is causing changes in response to drugs that we and that in itself we might not really have a control over, but there might be precipitating factors that are leading to that. And that speaks to the second point, where we're now in counterfeits for substandard treatment. When you don't use the appropriate medication, or the medication is counterfeit, doesn't contain the level of the active as should be, your final plasma concentration will be suboptimal, and that gives the plasma plasmodium an opportunity to develop resistance to that particular medication. And related to that would be unregulated or fully administered drugs. And as a pharmacist, this is something that we try to advise that once you start a course of treatment, it's essential that you finish it. Because of economic pressure, people want to get back to work as soon as possible. Once you start the treatment, and the treatment does give them some sort of symptomatic relief, they get out of there and out into the marketplace to see what they can do to earn a living. And of course, the first thing that gets out neglected is the medication that they take. And eventually, even though the medication might be up to standard, and because the cost of treatment was not adhered to, it will still lead to a situation where there will be resistance. And combination of drugs has also been suggested as a use the chance of the plasmodium development. When artemisinin came up, we were very excited about it, but eventually it was discovered that needs to be used in combination with methotrexate, as we used to have with vaccine, vitamin, and the rest. So combination, complementary action medication is important, and where that is not done, we also open the door for the organisms to develop resistance. So I just highlighted some of the drivers of resistance of malaria. There have been a lot done in terms of one of the things that we in the early stage, like remember laboratory system is insecticide treated nets. Majorly because of me causing this. And that way we could prevent being bitten by mosquito, which is the main transmitter of the plasmodium. So that came out, I think, with a program called Robot Malaria way back. But access to that net is still not universal, as it were, I would call it. Now, the second strategy has been, indoor spraying and the rest of them, trying to see where these mosquitoes stay within the building, within the houses, and trying to put insecticide and chemicals in those places, to stop the life cycle within those places. And predominantly on stagnant waters, and they really flourish in stagnant. So that's been another strategy in many areas. But even though we go indoor spraying, if you have stagnant waters and enabling them, conditions outside the house, they still breed, the mosquitoes still breed there. They still find their way back into, especially when there's no net spraying and the rest. Seasonal malaria prevention, prevention, so they introduce as a way to prevent. So this is aside the fact that if you're traveling to an endemic zone, you need to take a preventive medication, but they have seasonal strategy. And the most recent, which I've been working on for a long time, the advent of the vaccine has shown very much it's compared to what the previous result has been. It's been an exciting result, even though the response in terms of immunology response not so close to 50% or so, but it has been welcomed by the WHO, especially for children under 5, to use this particular vaccine to prevent malaria. Now, to put all those preventive strategies together, and in an ideal situation, they are applying, we should have elimination of malaria. And some countries have actually been able to eliminate malaria. And I look at this image that I showed you, and I see one of the things you see that if you compare this to the one that I showed in terms of the resistance, the Africa is now not having enough areas that are full of malaria. So it's kind of contrast to what I showed earlier. So we are not at that point where most African, some African countries are it, but not everywhere. It's the recent one. Kudos to them for what they have done. but a lot needs to be done in most Africa in order to eliminate malaria. So in terms of elimination strategies, I spoke about those prevention strategies, but what has come up in recent time is what called a reactive strategy. In the sense that if you spot somebody that has malaria, what you want to do is be able to say everybody around, that will play contact tracing, and everybody around that will be tested if they have malaria, or if the malaria transmitted to them from that person that is currently showing symptoms. And so you need to track those people and treat them. You need to come in and spray the area and begin to implement those prevention strategy. And that way, the WHO hopes that we are able to meet the situation in the board and stop the spread of that particular malaria within that community. There have been a lot of discussion around that, the logistical issues in terms of implementing the reactive strategy. But if well funded and implemented, is one strategy that might help to eliminate malaria. However, let me point out that effective anti-malaria drugs are central to this strategy. Even if there are people, even if you want to do pepper prevention, it's important to have effective malaria drugs to treat. Okay, now just wrapping this up by looking at the strategic framework by the WHO. I'm trying to link what we are doing here at this workshop to some of the key roles that are in that strategy. And I was able to spot 4 things: the research for prevention and diagnosis of treatment of malaria, really focusing on supporting basic research and capacity development. I really want to thank the organizers for aligning themselves with some of the strategies. Okay, cool. I'm switching chair now, moving from the emotional thing that I want to talk in terms of malaria, and looking at the ethnobotanical heritage, the natural product that we face. And for me, that I've used it for a long time, and I still tell my children they don't like it, but I have a couple of herbs in my fridge that I put together that I still use regularly, not for malaria purposes. So we have this. We all know that we have grown up in the malaria endemic area. There is one thing or the other that is putting for malaria, hypertension, or so many other infectious or non-infectious. Yeah, ethnobotanical heritage from our families. And I also, at this point, want to acknowledge Fidele and his team. We've done a lot in collecting some of the chemicals that are present. And to me, these are the resources. For example, when I did my PhD, these are the resources that I could tap into to begin to explore, these things that are out there. A lot of people have done a lot of work of, fractionating this, getting these biochemicals out, and really testing them and really now saying, going forward, can we develop this into, effective drug for treatment? And I think I try to do my bit in that space, and during the PhD, trying to see when we find those biochemicals that have been tested against plasmodium, what are the chances that they will become a drug? And if we do some sort of characterization, specifically looking at bioinformatics characterization, to identify the ones that are likely to be developed into drugs. We also look at the scaffolds, the unique scaffold that they have. I'm trying to see from the scaffolds for exploration, developing, and if there's a need to do a synthesis, what will be the synthetic pathway, and also to see can we make this unique, because the natural products are very unique scaffold. The nature makes that sometimes very difficult to make in the lab. And another thing that we did was to see that by AI space, Because when we talk of data, we need to show bioactivity. We don't take those set of data and build models around them. We can have AI models, genetic models that can predict bioactivity once you have the chemical structure. So if you think about the database that you still have, you can actually create those kind of database if you are doing an initial hypothesis generation for your studies. And I think Miguel and also be talking about the kind of algorithms that they have to look at AMR, antibial for anti-malaria. So that these are pre-designed models that for us to bring those available data. All right, so I'm going to talk about the case study, and because in this case, I'm looking at we have this natural product, we have development of resources, and I want to marry the two. And I must say, not only this, bioinformatics is also developing in terms of omics data that allows us to understand the content more. And that also we have leveraged into the space in order to advance drug discovery from our natural product to secondary metabolites. So in this case, I'm using this as a case study, anti-malarials, particularly pyrimethamine and guanine that is institute converted to guanine. So these drugs essentially target this enzyme, the hydrofolate reductase, which is the biofunctional enzyme linked to regulate synthesis. Essentially, what the DHF does, what it does is transfers nitric ion to that hydrofolate, forms the hydrofolate that is required by the plasmodium to form the part of the DNA synthesis. And so by stopping that particular enzyme, you stop the generation of the prime parasite of the essential folate acid to execute that process. So, and this medication was these drugs were working up to the time when resistance were developed against them. So, and this resistance were due to stepwise mutation within the target enzyme. So far, two mutations, double mutants and double mutant identified within that particular enzyme in plasmodium, and so called being their mutation 4 points and double mutation at 2 points within the protein sequence. And the studies have shown that these mutants are actually more active than the wild type enzymes in terms of the fact that they can actually proceed to generate the glycofolate enzyme faster than the wild type. So what we did was the student did, basically this was done in collaboration with University of Menace University in Nigeria. So the student collected biochemicals from major plants that have been used for malaria in Nigeria. I've used quite a number of this as a relator indicator. We have used a lot of that, and lemongrass also used quite a lot of that also. So they looked at the literature databases like the Fidele and still has, and find out what are the biochemicals in this, and just collated these about 200 biochemicals, and we stored them. Then we looked at the enzyme itself and tried to compare the wild type and the double mutant and the polygon mutants. In terms of sequence, just to check where the body is already been reported, just to check where they have the faster sequence of the protein. So we do run the sequence, multiple sequence alignment on cluster W, and that gives you the conservations and the areas where mutations are. And we also look at can we just align the structure of the protein and see what is the difference, and that's kind of reveal towards the double mutant, for example, it was not so much in terms of deviation from the wild type. The RNA was about 9, but the double mutant was a bit more in terms of structure far from the wild type protein enzyme. So, in order to characterize them, we did a couple of predictions using the Schrodinger matrix. And we calculated a couple of things looking at the surface area, positive, negative surface area, the donor acceptors surface areas, electrostatic sufficient energy. Now, all this play a role in the ability of that particular enzyme to bind a particular ligand. I'm not going to go into the details, but we still writing the paper. I think they already sent out on this to read, and you can get the details from that paper. But the essential thing is that you need to understand what you're dealing with here. We don't want to understand the mutants and we want to understand the wild type and what are the differences amongst them. So it's reported that the reason there's resistance is because the binding affinity of the metabolic to that binding site of that particular enzyme reduces as the mutation occurs. So I'm showing here the pyrimidine binding to the site, and I've already called some essential amino acid that it interacts with. Particularly, okay, so I think it was okay. 108, serum 108 that has a binding energy of about 1 kilocalorie per mole when you look at how it interacts with that. And serum 108 is one particular residue that is constantly being changed amongst the mutants. So if you go to so this is the wild type, and if you go to the double mutant, and you go to that and you check that particular 108 position that is changed to serine to arsenic. So you see that has happened, and we observe that the binding to that has changed also from 1 to about 0.5, and when we also look at it within the polychromosomes 108, which is still remain as that, as also about the same, but there's other changes within the other residues that changed the binding of that particular pyrimidine to those residues. So the idea was to say, okay, these are the things that has changed, and when we want to design a new drug, we need to find out to enhance interaction with these particular residues, and see how we able to circumvent this resistance. So I'm not going to go through what we did, but I'm looking at some answers workshop. So basically, just showing you the results from the workshop to tell you best practices when it comes to all this. But what we essentially saw was that 1, 2, 3, 4 biochemicals showed slightly higher binding affinity to the enzyme than pyrimidine, especially if you look at the two mutants that we studied. So that gave us some sort of an idea that can we look further into this particular chemicals. And when we did that, we said, okay, let's look across the mutant going from the biotype to the double mutant, the polymer mutant, and now not using the virtual screening, a bit more precision and docking, and see what we observe. We saw that the rosmarinic acid came on top in terms of its ability to bind to all the enzyme from the wild type to the double mutant to the polymer mutant. So it's kind of outperforms the rest of the phytochemicals. And so we said, fine, let's go on and see what it looks like when it's divided to special questions on the dynamics, which you're familiar with. I'm not going to spend on that. I'm just going to show you what in terms of results for that. Right. I'm sorry. Go back. Right. So in terms of results, so my particular interest, yes, people here are PhD and carrying the same interested. My particular interest in this case was to see what is the binding energy, how does the binding energy change over the trajectory when you do the molecular dynamics. And in terms of, yes, molecular protein did reveal that phosphoric acid better interaction. But what happens when put in all the system and do the molecular dynamics? So what we observed was that for a particular, I think this was done for the double mutant, what we observed was that rosemary acid still outperformed butyrate and pyridoxine in terms of the fact that over the trajectories, the binding energy that is summarized here was about minus 140 per mole, kilojoules per mole, with a standard deviation of 2.6 across that. And if you compare that to pyridoxine and compare that to butyrate, you can see that it's very influencing. And there's a very ability than butyrate. And so we were happy with this. And that brings me to my conclusion. What next? And the question is from workshop to action. I really want to also kudos to Fidele. You publish every workshop that I've been part of this, and I really want to applaud you for that. But I really, at the end of this, we also want to see in the past few years, having trained people, how many people are actually putting these things to use, and without really forcing people's hand, as there been acknowledgement to the fact that I learned a couple of skills here and I applied it in my research, either my PhD, my master's, or a publication, and that is what I've used to advance this particular research that I'm doing. I think that indicator is something that we need to do to see that this function is being put into action. And so that's one thing. And the other thing for us is that we need to start speaking to people that are not empathy. Another field in terms of people that are conducting vitro experiments to begin to say, how do we verify some of our predictions from our computational studies that we do? And I think building that network is also an output of this kind of workshop to say, who do I work with? And I do advance my research beyond where it is now. I don't want to publish within this space. I want to be able to push it to the frontier of my research and get to the next level. And I'm looking forward to that time. I'm also very, very open and still learning to really working with everybody and anybody in order to advance in terms of health coverage and achieving that particular goal of reducing particularly deaths among the underprivileged for malaria in particular. Thank you so much, and the organizers. I really appreciate your time. Thank you.
Thank you very much, and also thank you for leaving a lot of time to answer questions. And I hope that there's discussion and people would like to know more about your work. So I would like to open the discussion. You can raise your hand, or you can just in a minute also type your question in chat. When we wait for that, maybe I would like to start a little bit fascinating for me to see that well-known compounds, substances are still exploited in your work. So, like rosmarinic acid or the flavonoids are also so. Can you comment on that a little bit?
So you said I didn't get the
I'm wondering why you have so many known compounds still considered in your work for that phenomenon, for malaria, for this enzyme.
Okay, yeah. So I think the bias will come from the screening deck. So in this particular case, we selected the plants we're choosing the plants used in this country. And now that's not to say that that is all expressing on this. But a lot needs to be done in terms of really getting out some of those things that are really natural products, heritage. But simply put, one of the principles that we try to do, that we need to adhere to, is that how this particular extract, other extract used, most times they are aqueous extract. And because they're aqueous extract, there's so much you can get with an aqueous particular plant. And if they are practically achieving the effect, and we find out what is present in the aqueous extract, do they can we justify why they are having the effect? And if you justify why they are having the effect, this is outside this conversation. I'm looking for a situation where we can take those extracts as it is, go to the refuge of friends. We've proven that they can work. And we prepare this as some sort of a supplement for my medicine. I mean, the one route is to go and discover new compound from them. Another route is to say, and I put this together as a bouquet of compounds and use the supplement. And that's also been my passion. Yeah.
Thank you. So there's a question from the chat from Marko. How were the binding energies calculated that you presented at the end of your lecture?
So the study was done in MP mode. So during it allows you to calculate the interaction between the ligand and the protein. But I think it's just one script that you need to write. And it allows you to set measure the interaction. So typically what more is to calculate.
And then maybe the next directly related to that, did you only do free binding energy calculation?
Yes, it was free binding energy calculation. We didn't do those what we call it was MTBSC.
Fidele, do you want to ask the questions yourself?
Okay. I would say basically my question has to do with the mutation from serine to asparagine. Did I get it well?
Yeah.
Did I get it well? Was it a mutation from serine to asparagine, right?
Yes, I think it was asparagine, yeah.
Yeah, these two amino acids look very similar. It's just one functional group that makes a difference, and then one carbon atom extra. Now, how does this affect the resistance? Is it by modifying the backbone of the protein, or by modifying the side chain?
Yeah. So one of the questions I asked myself, a very good question, when I did this, was to say, okay, can I actually monitor the interaction and the flexibility of each amino acid residue that I implicated? That I haven't done, and that I think that will answer your question. And say, if the circuit was there and asparagine was there, what happens? Can I compare the trajectory and see how that affects? If they are actually available for the drug to interact in terms of So that was interesting. I don't know that. Let me see. Not
Yeah. Yeah, I would make a suggestion. Yeah, maybe I make a suggestion at this point that maybe if you have something, if you have access to Discovery Search Studio, there's a possibility of doing residue interaction. Yeah, the interaction between every single residue around binding site and this compound, and we see if there is a significant difference. What do you think?
Yeah, I think putting the master should be if I this one more than that. But I'm sure the master should be able to do this. That's very well noted.
Yeah, there's a question from Jonathan Mitchell. Jonathan? Okay.
Can you hear me?
Yeah.
Yeah.
Hello?
I can hear you.
All right. If you can hear me. The chair asked a question. Why do you consider known compounds in your study? I don't know whether you address that appropriately. Because we asked the question, compounds which are already known, why do you include them in your study? I don't know whether you address that issue appropriately. But I guess you use them as reference compounds to test the new compounds you have. Let me just finish so that I hand over to you. The question in my mind is this: in your study, you use binding energies to select their compounds against their target protein. Now, apart from binding energy, what other consideration do you take which will make you not to follow the binding energy criteria?
Okay, thank you. So let me address the question. So like I said, the goal here, the ultimate goal for this research is to show that these harmful products of this plant that we're using contain phytochemicals that have shown activity against this particular. Even when they use that in the way they have, they show activity against malaria, we know traditionally they reported. Now, if we go here and say, what do they contain? And they will contain common things. My guess is not to discover new things as well. The common thing that they contain, what are their chances that this is sort of explaining, kind of getting insight into possible mechanism of action of the common things that you refer that are present in there. And that way, we can work backwards and say, all right, if they contain those things, it's kind of begin to show evidence that this is how they work, this is why they work, and can we now table these plants that contain those things to the regulatory authority, and looking from a pharmaceutical perspective, and now use them as herbal supplement for that particular disease. So that's the aspect that we were looking at. The other aspect will now be you're talking about, okay, we want to now say, if I want to design a new drug, I'll probably not go this route. I'll probably try to look at the particular protein, look at the residues as discussed now, and begin to say, can I design something that will circumvent the current mutation that I have within that? Then I will come up with a new compound. And I do discovering a new compound and getting that registered and extended 10 years. I don't think we have 30 years for this. So that was our focus. Yeah, I'm very, very passionate about that approach. Then the second question you were asking in terms of methodology. Yeah, so we weren't really particular about, let me not say that it was a bit more rigorous. I think the student is still working on it. Like I said, the paper that I'm still working on. So one of the things aside the climate energy that you can do, of course, you can take from the normal energy go to MTBSA and the PBSA and that. And sufficient energy and the rest of them, and see the impact on that. On that. And what we did was to say, can we take it from beyond the virtual screening and to a more precision screening, which allowed us to say, even more rigorous in terms of our selection, and a little more computational intensive when we ran that. So those are the things that we essentially do. But essentially, the idea is to say, can we show that these compounds have the ability across all the mutants to show some sort of binding ability across all the mutants? So that was the main important, that was the main goal of this particular study. The one that is still ongoing. And with ultimate goal to say, this, we are to show that these things might affect this particular enzyme that is become resistant to the common medication that we have. And can we use this plant that contains this thing as a supplement for this particular malaria? I hope that answers the question.
Maybe, I don't know how we are doing in time. Maybe we have one more question from the chat. Basically, two questions concerning the same thing. Are molecular docking studies possible on a mixture of two molecules? Or can we do molecular docking to check synergistic effect? I think these questions basically concern the same thing or the same question.
Yeah. So if you look at the data that we have and begin to analyze that, so you really see potential, an adult supplement that contain multiple phytochemicals. And they have phytochemicals that are acting against certain pharmacology, we know they are acting against multiple targets. And so polypharmacology tells us that. So we know that it is multiple targets. So the advantage of our natural products is that they are already synergistic. They might be synergistic in the fact that they might be acting against two phytochemicals acting against one particular target. That enhances your activity. But down the line, you might have a situation where another enzyme is being either activated or doing something. So it's a real complex situation. So what I'm proposing to my approach to the scientific community is that, can we understand what all these phytochemicals are? Once we understand what they're doing, let's bring all the data together and begin to map this into some sort of a network so that we know where they are acting, and perhaps we can now walk backwards to begin to understand what is driving the activity that we have in our products.
Okay, thank you. Fidele, how are we doing with the time? Can we have another question, or should we stop?
Sure, we can. It's getting really excited.
Yeah. So I really don't know who was then next. I see two more questions in the audience. Jutta, maybe first.
It was not good.
Well, I'm sorry, I didn't really see the line, but anyway, who wants to start? So there's Lloyd and Jutta.
Yes, thank you for the thought. So I just want to ask you one question. First of all, what about the nature of the mutation you analyze? You say in your presentation you analyze the double mutant. For these drugs, we have different type of mutation associated with resistance for this drug. So I want to know about the mutation you analyze.
So in this study, we give it analysis to the double mutant and the quadruple mutant that have been identified. Particularly, of course, because the structures were present in the protein data bank that align with what the tools and the strategy we wanted to use to to answer the research question. So that was what I did.
Okay, thank you.
Okay, so next question.
Can you hear me?
Yes.
Thanks for the presentation. I wanted to know about what are the other ways, because docking should not be the only way to docking and binding free energy calculation should not be the only way to understand how they are binding with the protein. Like molecular dynamics simulation obviously is another way, but have you about using UMU study or which like a reaction based, like mechanistic based studies with like experimental verification, like kind of synergistic or combinatorial study to verify your results?
Okay, yeah, thank you. So I think that's what I said at the end in terms of verification. These are predictions, and I think this to start looking at how to collaborate with people. So one of the papers, the authors that we have tried to write to, we've written to collaborate with, the people that showed that this particular mutant different activity. I think I posted one of the papers on the slide. So we try to reach out to them and see, okay, can we already to show the activity of this particular enzyme, and they can actually insert mutations within the enzyme before testing the activity. So we've written to them and say, okay, fine, can we use your platform and collaborate on your platform and be able to verify the effect of this potentially new inhibitors in the activity of that particular enzyme. So that is one thing we are looking at. You're right, of course, that will be the ideal thing to do. Say, I don't predicted
the reason why I was asking was this because most of the bioactive compounds have stereochemistry, like unique stereochemistry, especially in bioactive. So this will get more like how this interacts with the binding, because in molecular docking they try to adjust and the stereochemistry is not the, I will suggest in most of the protocols don't accommodate stereochemistry very well in the molecular docking simulations. So that's the why I would find that this would be done in like a combinatorial fashion to really validate your predictions.
Yeah, I agree. And one of the things that we also observe, especially when it comes to really getting the conformers right, is you saw a significantly different result when you use QM
Yes.
to do the trajectory, and that's though a bit more computationally intensive, but in recent times we've seen that it's
But
important.
presently there has been some AI based which reduce, like they can do in a smaller, like relatively smaller theory, like lower level of theory, and then predict for a higher level of theory. So you can substantially reduce this kind of lag with some AI models which are already published on this kind of thing.
Oh, that's quite interesting. We'll look out for that. That's quite interesting. No, thank you so much for that. Thank you.
Yeah, thank you very much. I'm not sure we may need to stop here. Yeah, we have a really good discussion going on, and I believe that we have a lot of different ideas now to bring back home or back into the lab actually. And I believe before we continue with the hands-on sessions, there's an announcement for a change in the program. Fidele?
Yeah, apart from the next hands-on session we have after the short break, we have already eaten up part of our break time. Marko, Dr. Marko Jukic is supposed to be the first speaker tomorrow morning, and unfortunately he's not available tomorrow, and he wants to give his talk today. It's 20 minutes talk, and he's willing to give that talk after the hands-on session. So that's the first oral presentation. So after the hands-on session, we will converge to get that talk. That's the only change in the program. And so tomorrow morning, he's going to be replaced by someone else.
So please come back after the hands-on session to the main room, to the main conference room, and then we are looking forward to hear about the computational applications.
Yeah.
Thank you.
And also we have the hands-on sessions are going to break away from here. So there's already some links. So you can look at the chat and you see the links to join the hands-on sessions. And I will stay in the main session to answer any questions that come. Yeah. Enjoy your break.
Hello. Can you hear me? Can you hear me now? Hello? All right. Yeah, apologies for small technical difficulties here. So I've managed to join. I would like to thank you for joining here today. I hope you've had a great start of the session. And my name is Yannick Djoumbou Feunang. I am a data scientist, a senior data scientist at CodeHeaven in the US. And today I'm going to provide a quick hands-on session. We're going to explore an antimalarial drug through chemoinformatics and QSAR. because of the inability to send my instructions before the working session, what is going to happen is I'm going to do a live demo, a live session here where I'm going to go step by step through the different phases of this process, and I am going to be sharing the code via a link later. So I will provide the URL to the link to my the organizers, and those will be shared too. That way you would have some examples of how to run this type of analysis. It's a very it's going to be a very basic set of tutorials, but then with additional links so that you can further explore the concepts that I will present here. So, and let me know if you have any question. Feel free to interrupt. And if you can't hear me for whatever reason, please feel free to let me know. Thank you. So, a brief presentation about me, brief introduction about me. So, I was born in Cameroon. It's where I studied for the first 16 years of my life. I earned my high school diploma there, particularly in Douala, for those who know Cameroon. And I went to Germany to study. So I obtained, my B.Sc and M.Sc in computational biology and computational chemistry. And then I traveled to Canada for my doctorate. That's where I started exploring chemoinformatics with application in biotechnology and metabolomics in particular. And after a short postdoc, I went to the US. So as you can see here, a few tools that I've developed along the way to classifier for structure-based classification, automated classification of chemicals. You might have heard of it. Biotransformer for metabolite prediction. So feel free to check those tools, and CFMID for the prediction of spectra, starting from compounds and also compound identification. You might have heard about the drug bank database, about the human metabolome database, and also the toxin and targets database. Those are projects that I've been part of while I was in Canada. Currently, I work for a company that specializes in agrochemical discovery. But here today, I'm going to be representing myself and not the company. So the views that I express here are mine only. So I recently moved to the Bay Area in California. So I'm working remotely from there. So if you're interested, a few of my hobbies as Cameroonians, that's something that is not so, unheard of. So we are a lot into music and soccer and basketball and all that. So that's for me. And today we're gonna, work towards the discovery of new entire malaria product. Obviously, we're going to use an assay that rely on already tested compounds. But what we're going to do is build a model to predict compounds that have not been tested before. So you've heard about malaria earlier today, so I'm not going to say too much about it. As you know, it's a disease that is affecting a lot of people. But for those who live in tropical regions, the likelihood for you to have experienced the disease before is quite high. I've been a victim of it myself. As you know, it's transmitted between people via infection of infected mosquitoes. So the bite of an infected mosquito will then enter the victim's body and travel into the person's liver, and that's where it will reproduce, and the disease will progress unless stopped. So it can easily lead to death. So that's why it's such a critical condition to find cures for. So with respect to the drug discovery design, and in particular computer-aided framework, we could simplify that design as a heat, or that design process as a heat to active to lead. process. So a heat usually is a compound that passes a certain activity threshold. For example, early binding, binding against a certain target, right? So an active is synthetically actionable. And he has activity against the target, but we can also quickly weed out or remove the ones that don't show an unwanted mode of action. So if the molecule is hitting the target of interest but also hitting a bunch of other targets and leading to toxicity, these type of molecules can be weed out early on. The lead usually has an activity profile that is significant enough. So it might be a novel molecule that is not been discovered before, or a molecule that is outside a certain protected, IP chemical space, and something that warrants significant involvement. So, and depending on whether we have accurate information about the protein target or not, scientists will use several methods to maximize the likelihood of the discovery of new heat. So in best case scenarios, you will have, the ligand structures and you have the structure of the target, but also maybe ideas about known ligands, right? And then you go from there to design new ligands, or you will be able to dock a bunch of structures into the ligand of interest, and then select the ones that bind, and then from there you will further filter those molecules to prioritize them, maybe by physical chemical properties or by additional activities or by toxicity, and that you can use. You can filter those molecules using predictive models, for example, and that's why it's important to have predictive models on top of things like docking stations, visual screening stations, right? So in crop protection, where I currently work in, the discovery in the earlier phase is mostly following a ligand-based design. So we don't even know the target. All we know is that, okay, we have a compound or a known ligand, either based on, literature research or hypothesis. We have a ligand or a scaffold that is able to, kill the pest of interest, or a pest that is, genetically closer to the pest of interest. And starting from there, we will then, build or find ligands or molecules that look similar in terms of shape, for example, or that have similar profile in terms of certain specific properties. And that's where we start hitting, the QSAR models, and then filtering those molecules away that are toxic or bad. And then we will pick, the ones that are more interesting and go for further testing. So I'm going to briefly, illustrate the drug discovery pipeline here. It's similar to the agrochemical discovery pipeline. One thing that is very important to notice is that the molecular discovery or small molecule discovery pipeline, whether it's pesticides or pharmaceuticals, they follow an iterative design, make, test, and analyze concept. So it's something that starts with designing the first set of molecules. As I mentioned, it could be through docking or into screening or de novo design, and then they are synthesized in the make phase. They are tested in the test phase, and then they are analyzed in this case, this is where, as you will see, QSAR modeling will appear. So in the design, you can use the ligand, the structure or fragment-based model, where, as I mentioned earlier, you design new ligand, or you look for new molecules based on known actives, right? Or the structure-based model could use the structure of a protein of interest, or information about the binding mode of known ligands of that protein, so pharmacophore constraints and things like that, or binding pocket information to design molecules that would fit into the pocket. And obviously, the idea is to optimize the molecule so that it can reach multiple objectives. It has to, adhere to the right ADME properties, so it has to, be absorbed properly, distributed properly, metabolized properly, and excreted. But it also should not be toxic, and at the same time, it has to hit your target of interest. So now, the make has to do with, finding. So this part has to do with finding the correct route that will lead to you building the compound, right? You create the compound, and there is a huge field now that aims at building software and predictive models that will take the molecule of interest and, starting from a library of building blocks that you have in store, for example, tell you what are the best routes, what are the best conditions to generate the molecule of interest. So then you test the molecule, right? So you test it against your target, against associated target, against targets that you don't want the molecule to hit. To hit. You will test it, for you measure some physical chemical properties like the solubility or the lipophilicity and so on and so forth, and then you capture the data. Then after capturing the data, you have to analyze it and make further hypotheses to come back and maybe optimize the molecules for additional design. So in analysis, you have the QSAR analysis, the SAR analysis of structure activity relationship analysis, and that's where you take advantage of the data to build models so that you don't always have to go through these expensive tests, right? And then you also learn about toxicology, and then you can also learn about metabolism or environmental fate of your molecule, right? So with all of the data here, you can build models to then assist you in the discovery or the design of the better molecules, right? So, and as you can see here, it's an iterative process. That's where QSAR is applied in the analysis phase. So what is QSAR? Basically, QSAR is a modeling technique or a modeling framework that aims to establish mathematical relationships between structural properties of a molecule and its biological activity. So it usually provides a cost-effective and efficient way to estimate the activity. Now, generally, when you start with this drug discovery campaign or small molecule discovery campaign, it could be a drug, it could be drug protection agent. It could even be a molecule for cosmetics. When you create fragrances, sometimes those are actually made, right? So you want to start with a huge number and then find the most appropriate molecule. So you start with hundreds of thousands, if not millions, sometimes tens of millions. We're trying to go into billions of molecules that you start from, because the space of chemically feasible molecules of interest is about 10 to the 60. So that's huge. So what you want to do, you cannot test all of them experimentally, even through hard screening. It's not going to be sufficient. It's going to take you centuries, right, to be able to do that, and it's going to be very expensive. So QSAR models provide a cost-effective and an efficient way to estimate the activity of molecules. And it reduce the reliance on the expensive time-consuming experiment, or delays it, down to later stages. Now we have QSAR. We also have QSPR. QSPR stands for Quantitative Structure Property. So this framework does not just allow to detect, for example, if a molecule is toxic against humans, or if a molecule binds to a certain protein. It can also allow you to guide or estimate the certain properties, like let's say lipophilicity, for example, based on a number of different descriptors, as we will see later. So QSAR modeling, as I mentioned earlier, helps researchers to prioritize the candidates for further investigation and development, and it focuses the research on the molecules that are most likely to be successful. So you want to start with the hundreds of thousands, if not millions and hundreds of millions of molecules, down to maybe a few thousands that you are going to focus more. So those thousands you can then put them through high screening and then get the real data. And as you progress, the pipeline needs to be smaller and smaller and smaller, right? The pipeline is going to be smaller and smaller and smaller, and then you're gonna get down to maybe a few tens of molecules that you are going to push through clinical trials, for example. So the negative design here removes the undesirable compounds like earlier on, and then the positive design selects molecules with that property, right? So the QSAR models take certain types of information and transform them, manipulate them to produce another type of information. So the molecules are generally represented in various forms. So you can represent it in SMILES notation. That's a one-line notation that is very useful. It's the most standard, the most popular representation because it allows you to have an idea of what the molecule looks like. Of course, it's not as clear as the graph, but at least for the sake of ease of manipulation and also even for natural language processing, the SMILES is very, very powerful. So we also have fingerprints. Like fingerprints provides an abstract representation of the functional groups or molecular features that are present within the molecule, right? So they are usually of fixed length, and they can be predefined. They can be based on structure. So you can have, for example, a list of 10, 20, 100, 1,000 different structures or structural fragments that you have identified as important to large-scale analysis. And you define each bit here for each of those structural keys. For example, the first bit will be indicating whether the carboxylic group is present in the molecule or not. Second bit will maybe indicate whether a primary amine group is present in the molecule or not. And you could decide to just identify presence or absence with ones and zeros, or you can decide to count. So it could be 2 carboxylic group, 1 primary amine, and so on and so forth. So those are things that you can try when you're doing your predictive model. You're going through your predictive modeling project. So those are fixed, as I mentioned, but they are also learned features. They are learned from semi-supervised or unsupervised learning, right? So you probably heard of deep neural network. There are other methods that are not necessarily deep neural, based on deep neural networks that can allow you to take molecules and represent them into a set of features and provide a mathematical representation of the molecules. But those are not fixed. So depending on the data set, they can, even if the vector representation of the molecule is the same length, the content can change, right? Because it will depend on how much molecule you have in there, how diverse the data set is, and so on and so forth. So I'm not going to get deeper when it comes to learning features. But we will focus on the classical machine learning. You can also combine both. So for the sake of expressivity, especially if you have a good estimation of what properties can be very important for your specific needs, for your specific target or endpoint, you can add or combine learn and fix properties together for better performance of your model. Now, the classical operation in predictive modeling includes, the data collection. Obviously, you need to get the data from somewhere. This is a very critical part. Sometimes we are so excited about creating a model that we forget about the quality of the data. The data quality is very important. We usually say garbage in, garbage out. If you put garbage data in, that is not standardized, that has a lot of wrong values. You have duplicates, with different measurements. I've seen cases where, usually when you're doing, you're testing your molecules, you want to try maybe twice or 3 times for the same molecule. You might select a few molecules, when you have, a million of them or, 10,000 of them. You're not going to replicate all of them necessarily, but you might want to try a significant number that you replicate, right? So that allows you to then measure the standard deviation and also understand how reliable your experimental setup is. So, and I've seen cases where because of the experimental setup, because it was not very appropriate, you will have a molecule, for example, that, an assay that measures the degradability of a molecule in soil, for instance, right? And then one of the measurements for the same molecule would say the molecule is degrading completely, and the other measurement will say the molecule is not degrading at all. So that's a significant problem. So you want to remove these examples, right? But you also want to question the reproducibility of your analysis. It's of your experiment. So if the experiment is not viable, if it's not reproducible, you cannot expect the predictive model to do any kind of magic here. So that's why we say garbage in, garbage out, right? That is very important. As a matter of fact, the overwhelming majority of the time spent in predictive modeling is spent in data collection. So once you've done that, you split the data. Usually you want to train the data, the model on a specific set, and then test it on the set of molecules that were not used for training, right? So you want to make sure that it can generalize, because the idea for you is that you're going to train it on some molecules so that you can test it on other molecules for which you don't even have the results yet. So to be even more precise, or to increase the chance of having a better model, right? Well-performing model. Instead of splitting into tests, we will split into train, validation, and tests, right? So during the training, you will train on the model or the training data, you will validate it, and that's usually helpful when you are doing like a parameter optimization, or when you're training several models, right? Training over time. And then at the end, after you get the best of the models, then you can test it, right, on the test set. So then you select the model and train. You can select, different type of algorithms. You can go with deep learning models. You can go with, classical machine learning models. You can even try, make all of them together. Not every single architectures, but various architectures, deep learn or classical, right? And once you do that, and you find the best model, then you have to validate it. Again, you validate it on the test set. Don't be confused here when I mentioned validation here and validation here. Here, this validation set is during the training, and the test set is where you actually validate the molecule on external data. You need to understand what the metrics are, select the appropriate metric, and that's what is going to be used for you to even compare models, right? So then, in terms of the application, you predict the biological activities on new molecules, and then you interpret the model if you want. It's usually a good idea to be able to interpret the model. So that will allow you to detect maybe the biases in the prediction. It will help you also, understand what features are contributing to, activity in general, for the whole set of molecules, or maybe for a specific molecule. Then you want to validate it again on some other data that, was never seen before. So here, you're working on data that you maybe gathered, over the last 5 years or whatever. Now, maybe in, 10 days, in a month, you have a new batch of data that is coming in, it might be a set of molecules that is not really similar or close enough to the molecules that you use to train. So that means they are not necessarily in the applicability domain of the molecule of the model. So you want to make sure that you can test those and see if the model is still performing. If the model is not performing, that means that you probably want to retrain the model to expand its applicability domain to this new series of molecules, right? So that's where we are. And I'm going to stop here and take any questions before I go to practical part. Is there any question? I hope that this will be kind of interactive. So please let me know if you have any question. If not, we're gonna move along. Okay, so the next thing that I'm going to do is I am going to share what we call a notebook. We will go through this together. It's not going to be exactly live in the sense that you're not going to be, running the code in parallel. But as I mentioned, I will share the whole data so that you can replicate the operation, right? So what we're going to do here is basically train classification models that can predict a compound or molecule's ability to inhibit the Plasmodium falciparum growth. And that will be the DD2 strain. So with respect to the minimal number of molecules, that's a great question, by the way. It's important to have as many molecules as possible. It's important also for the data set to be diverse. So you don't want all the molecules to be from the same series. You don't want all the molecules to differ just by a single, functional group or a single atom. So you want them to be diverse, as diverse as possible. I will get into it a bit later. The minimum recommended number of molecules, it really depends. So if you want a a model that is very low. So imagine you have found a scaffold, right? That is very active. You have a set of molecules that are from the same scaffold, and you want to generate additional molecules from the same scaffold, right? You might get away with just having a few hundreds of these molecules and building a local model. If you want to build a global model that is applicable to a large to really diverse set, you might go, you might need a few thousand, if not more. Now, it will also depend on how complex the endpoint is to model. Certain models are quite easy because of the simple relationship between the mathematical relationship between the properties of a structure and the endpoint, right? But there are others that are very complex, and for those you will need a diverse set. You will need to try, different methods of representation. You might need to combine, fingerprints with, molecular properties and so on and so forth. So, but we will get into that. So, I am using Python here, right, as a programming language, and the idea here is that we will use Python and associated libraries in order to generate, the model and to evaluate. Okay. So to accept a few people here before we continue. All right. So okay, let me see if I can Yeah, I'm going to increase the font size here. So, okay, so I hope that you can see very well here. So I'm using
Yeah, those who are on the main forum, I just want to announce that I'm now in the breakup forum, the breakup groups. So hands-on sessions 1 and 2 are going on. You check on the chat, you will see the links to join them. You can click and join the different hands-on workshops that are going on right now. Thank you.
I'm using VS Code. VS Code is an IDE that is very good for just text, but also for programming, right? For writing code and testing, and it has an environment that is really neat, right? So you also have the terminal for those who are familiar with Linux. You have a terminal where you can really do a lot of work. But I'm also using Jupyter Notebook. Jupyter Notebook is a framework that allows you for easy interactive programming, right? So instead of writing the code into a file that is difficult to read and whatnot, so I'll write the code into the notebook. But I have in this folder that I will share with you, I have modules that are written that can call some of the functions that implement some of the functions that I'll be calling in the notebook. I will also share a list of dependencies that you need to install before you can run this code. So, with respect to data preparation, first of all, I import the necessary modules here for processing. I split the project into two different parts: the data processing and the training. The training notebook will also contain evaluation, explanation, and so on and so forth. So I'm loading all the different packages that I need. Pandas is for tabular, so representation of tabular data. NumPy is for manipulation of vectors, matrices, for basically linear algebra. RDKit is the package the chemoinformatics package that I'm using to draw molecules, but also calculate properties, convert smiles to different formats. And I'm also using Modred. Modred is another package that implements several physical chemical descriptors. So I'm setting the seed here. This basically is the number that kind of control the operations, right? The weights, especially when you are doing operations that can, randomize, that can use random maybe to select or to mutate some object, right? So for the sake of reproducibility, you want to set the seed so that others can replicate the results, right? So next, I use Panda to load the data. So the data looks like this, right? The data is from the paper that was published earlier. Basically, they gathered the PubChem bioassay with ID 2302 that was made.
Yannick, excuse me, I can't see your screen.
You can't see my screen?
Please? Yeah.
Oh,
you are stuck in ask a question slide.
Oh, my bad. Yeah, okay. Let me do that. Yeah, because I changed. Okay, I'm gonna share this entire screen. I think I was sharing just the tab. My bad. So okay, so here we are. So just to summarize, let me know when you see my screen. Okay.
Yeah, it's okay.
All right. Thank you. Thank you so much. Thank you. So so you see it properly. Okay. So here is where I'm loading some of the libraries that will be used for programming. I'm setting the directory, where the code and the other folders are saved. I am importing AutoKit. I was mentioning AutoKit earlier, which is used for molecular operations. Basically, it's one of the most popular chemoinformatics libraries today. And here's where I'm setting the seed, right, to be able to reproduce operations. Here, I'm using Panda to read the tabular data. And these are the smart strings, right? You have the PubChem IDs, you have the primary outcome, and then you have the percentage of inhibition. Basically, the percentage of inhibition is what has been used to determine whether the molecule is active or inactive. Generally, here, if the percentage of inhibition is above 50, or is equals 50 or greater, then it's active. If not, then it's inactive. So when you're doing the cleaning, it is very important to, first of all, remove all of the samples. And the sample is identified here as a row, right? All of the samples that don't have a SMILE string. If you don't have a SMILE string, you don't know what the molecule is, right? So you need the SMILE. Yes.
Kiran, from my side, I cannot see your screen. I don't know if other members can. You can see Lucas. Oh, okay.
Yeah, and maybe you want to adjust your Chrome, or you want to log off and join again. I'm not sure what, but does anybody else have an issue? No. So okay, so we remove the line with empty smarts, right? So and to see how that is done, basically you can look at the clean data function in the preprocessing module. The preprocessing module is here. And again, I'm going to share the document. So I will provide my email address, and feel free to contact me at that address. And I will share the URL with all the the clean version of the code. So if you look into the preprocessed modules, because we in Python we basically create modules that contain, that encapsulate features and functions. It makes it easier when you're running your code. It's making it easier to debug, and you also don't want to have a gigantic file with 2,000 different functions in it. So you can group them by theme. I have one for preprocessing, I have one for splitting, I have one for visualization, and so on and so forth. So basically, what this thing does, this function, it takes in the data frame, the target column. The target column for our classification will be called DDS activity CLS, DD2 activity CLS, right? Or DD2 activity classification. Now, what's going to happen with the clean here, since I have active and inactive, I will want to turn this into ones and zeros. 1 will be for active, and 0 will mean inactive, right? So since we are not doing any regression analysis, we are actually just predicting whether it binds or not. We are going to remove this one. We're going to clean, obviously, the SMILE string. So, and sometimes when the chemists are, a lot of you here are chemists, so you will run your test. You will, usually the molecules or the substance will be salts. For example, you have sometimes a molecule or substance is maybe chlorinated or sulfated or whatever. So they will often report molecules that you see here. This molecule here, when you see the dot, it means it's a salt, so it's a chlorinated molecule. So you want to remove the chlorine, because at this point we assume that the activity is linked to the main molecule and not the chlorinated part. So what I'm going to do is I'm going to fragment the molecule, the substances here, by the SMILE string, and just get the largest fragment for each molecule. Okay, the largest fragment here. So, and then I'm sanitizing it, meaning I'm going to clean the SMILE string. So this SMILE string here shows a representation. So you have the carbon that is in a ring. That's why you see the number here. And then it's linked to another carbon using a double bond. The double bond signifies that it's the equal sign signifies that it's a double bond, and then it's linked to another carbon atom, and so on and so forth. So I'm going to clean it, put it in a way that is easy to manipulate later. So with respect to the labels, we have to check the integrity. So sometimes you will see duplicate. So you see some molecules that are, you see some lines where you have the same substance or the same molecule. Sometimes you may even see the same molecule basically, but it's different SMILE strings. So different SMILE strings, but it's the same molecule, and it's different. They all have different CIDs, right? So you want to make sure that you take one molecule and only one molecule, especially in classical machine learning, one molecule per one SMILE representation per molecule, right? So, and sometimes you will have replicates, as I mentioned earlier, and the replicates might indicate different outcomes. Imagine you have the same, or imagine, just for the sake of the discussion, that these two molecules were the same, right? And then you have one measurement says it's inactive and another says it's active. What do? If you only have two, imagine here, see if you are using the percentage of inhibition, right, to classify it as inactive or active. If, you know, the percentage of inhibition for the first molecule said 4, and for the second, for the duplicate, it said 80. Those are at, you know, the value, the range is between 0 and 100. You cannot have 4 and 80. So that's something went wrong. So you want to remove those, right? If, you know, one was 49 and the other was 67, usually you want to do an average, and it's going to be a little bit over 50. So that means you can see classified as active, and then collapse those two rows into one. Now, to be more strict, you might want to, you know, collect or group the data frame once you have cleaned the SMILE strings and created what we call the Ntie-Key. The Ntie-Key is a unique identifier, right? So this is the Ntie-Key of the largest fragment. Once you have all of those together, what you want to do is then group the whole data set by Ntie-Keys. So for some Ntie-Keys, you're going to get only one. The group is going to only have one instance. In some cases, you might have 3, 4, 5 instances, meaning that for the same compound, there were 3, 4, 5 measurements, right? And then you want to see what are the values, right? So you might identify outliers and you want to get them out. And if you remain with, let's say, 2 out of 5 molecules or 3 out of 5 molecules that have a range that our values are around the mean, right? Not too far from the mean of the whole data set, then you can just, you know, do the average and then use that as your value. Before then you assign whether the molecule is active or not. So I'm not going to go any further, but here it prints the number of rows with undefined label after we've cleaned the data is 0, right? So the number of molecules with missing SMILEs was 13. So we have removed 13 out of 13,533. That's why you will see later on that we have 13,520 because we removed those. Now, the number of unique Ntie-Keys, we have 13,520 molecule rows with valid SMILEs, but we only have 13,450 unique Ntie-Keys. That means, you know, a little bit over 50 or so, 70 or so are duplicates, right? So we're going to remove, I haven't applied the strictest application removal here, but yeah, so that's what we did here. Now, you have the number of duplicates that were removed. You have an example here of duplicate, right? So these are the indices or the compound IDs actually the indices of some of the duplicates. You see, the SMILE strings here might have been different actually, but then the Ntie-Key is kind of a barcode. It provides a unique identifier to molecules. So you can have SMILE strings that are different. That's the disadvantage, but also the advantage with SMILE strings. You can have SMILES strings that are different, look at them as synonyms, right? But they represent the same molecule. So that's why you want to compare the Ntie-Kangs here when you are looking for duplicates. So you have those two duplicates. Luckily, you know, they are all classified as active, so we are only going to take one measurement. And here, same thing, those two duplicates. They are all classified as active, so we're going to take, you know, just one of them. So now, with respect to molecular representation, once we have our data set, so what is going to be interesting to us is going to be from now on the SMILE string. Here, the largest fragment, the SMILES, I added hydrogens here. This molecule that we're going to use, right? The R-mol is the whole molecule without fragmentation. And here is the molecule object implemented in RNA, right? That is going to represent the largest fragment. So that's what we're going to use from now on. And the SMILE string, as well as the Ntie-Kang of the largest fragment. Now, with respect to the representation, I mentioned earlier that we can have fixed representations, learned representation. And here we're going to focus on fixed representation. So you have the constitutional descriptors, basically such as, you know, the molecular weight, the number of atoms, and you also have the geometrical descriptors. They basically are related to the molecular shape, size, and symmetry, right? So they describe it in various forms. You have the topological descriptors that are based on the connectivity of the atoms, right? Different indices. So they look at each atom and see how connected it is to others, and so on and so forth. So you have the electronic descriptors that are related to, you know, the density, the energy level, and whatnot. And then you have the constitutional or functional groups. So here, for example, you might be looking at the number of amines, as I mentioned earlier, the number of carboxyl groups, the number of, the number of nitro groups, and so on and so forth. So I have implemented a featurizer here in this module called featurizer. Basically, what it does is it takes a molecule and, you know, based on the user specified list of features, it will calculate all of those features and put them together for all of the molecules. So, for example, here I calculate the molecular weight, the number of aromatic rings, and so on and so forth. And a lot of these indices that have to do with the topology. I'm using Modred and RDKit for that. But also with RDKit, I'm calculating the number of occurrences of certain functional groups within each molecule, right? So it takes about 2 minutes to calculate over 200 features. Now, one interesting thing is sometimes you might have elemental features that don't mean that much, right? But by combining them, you know, you might have a huge signal here that is going to be, you know, helpful for modeling. And you can customize the features, right? In this case, for example, I added the number of halogen atoms and the weight ratio, right? In some cases, you know, it can be very important because halogen can impact the atomic properties of the molecule, right? So, and you know, depending on the scenario, in agrochemical design, for example, we say, okay, we want the ratio of the weight, the total weight of halogen atoms to be no more than 30% of the total weight of the molecule, for instance, for a number of reasons. The fraction of sp3 carbon is also very important. So sp3 carbons tend to be more hydrophobic. So when I say that, you know, you understand that they can, you know, impact the protein binding and so on and so forth. I also added, you know, a value, a Boolean value that tells if the compound matches is rule of 5 or not. So here is an example for the first 2 molecules of the data set. These are the values for the you know, the features that I added, right? Now, here I'm cleaning. So here, what I was doing was computing the properties, right? Here I was cleaning the data set before having all of this, the features. So I was just, you know, removing the bad SMILES strings, removing the rows with empty SMILES. Here I'm actually cleaning the data set. So I'm going to remove the values that are NaN I'm not going to standardize at this point, but I'm going to remove the values that are nil and do some additional work here. So you can look at the code in the preprocessing. And also, one thing that is very important, because we want to use as little resources as possible, right? So the data frame here was originally used with the floating number. For those who know a little bit about the arithmetic here, so it was using floating number with 64 bits. Usually, those are helpful when you are expecting really large values in your data set. Here, we're dealing with small values that can be represented with a smaller flotation number. So by that, I was able to decrease the memory usage. By reducing the memory usage here, I was able to gain about 74.6%. 74.6% in terms of memory. So I have more memory now to use for subsequent data compared to before calling this function here. Now, let's go to the fun part. Often you want to see what of your descriptors are really correlated with your target. So that might give you an idea of what features are important. But it's important also to note here that just because a single feature doesn't have a high correlation target, it doesn't mean that it's not important. Sometimes that feature might be important when you collapse it with other features. So the molecular weight might not be very important, for example, for a specific outcome, but when you combine the molecular weight with the number of bonds and number of aromatic atoms, number of, maybe chlorine atoms, maybe all of those together are going to form a very strong feature, right? So that's for the model to decide. So, but it's already really interesting to see that, for example, this topological index here is highly correlated. Obviously, the number of aromatic bonds is also highly correlated. So the higher and here I'm measuring the absolute correlation. So, so it could be a positive correlation or negative correlation. But here, just for the sake of comparison, I'm just looking at which ones are highly correlated to the target value, right? So the higher this value, the more correlated the feature is to the target, right? So, and another thing that I'm doing here is I'm plotting the correlation numbers for the added those 4 or 5 added features, custom features that I added before. So you have them here. Of those, the feature that correlates more is a fraction of sp3 value, right? Okay. Now, with respect to the visualization, the Lipinski rule of 5 is a set of a few rules that were determined, I think, later in the 90s, for that says that molecules that fit or that matches those constraints are, very prone or very likely to be drug-like. So with the radar plot, especially when you're comparing active versus inactive, gives you an idea of the distributions, right? Of the different values. So if you know how far or what is the range of the values, right? So this basically, the area here is basically the area that you're targeting, and sometimes the values might go a little bit above, right? So another way of visualizing the distribution of the functions of the descriptors is through box plots. Basically, the box plot can give you an idea, for example, of what molecules, what features, for example, are differently distributed between the active and inactive class. In this case, for example, when you look at the number of aromatic, remember earlier, it was a feature that had a high correlation, right, with the target value. You will see here that it occupies a fairly, so 50% of the values are within this box here in active molecules, right? So, but for inactive molecules, the values occupy a wider range. So that is an indication that the distribution is a little bit wider here, and it's an indication that it might be an important In some cases, the distribution are the same. Like here, for example, number of hydrogen bond donor, the distribution are almost the same. So basically, you have this endpoint. These circles, dictate or specify what the outliers are. But then you have generally the lower value, the higher, the max value outside of the outliers, and then this tells you the median line that tells you that 50% of the molecules have a value below this value here, this threshold here, and 50% have a molecule above. Now, in this case, also the features occupy basically are they distributed within the same interval. However, because the median line is lower, it means most of the molecules, right? Most of the molecules are pushed towards this higher part. And here, most of the molecules are pushed towards the lower part. Right? So I have within the notebook a lot of text to explain what I'm saying here. So don't if you don't understand one of the things that I'm saying, you can ask questions, but you can also I put quite a bit of text here to let you to help you understand the concepts here. So with respect to the functional group, you might also want to know which functional groups are very important, right? So you can do a plot. So here, what I did was I, looked at, the occurrence, the number of occurrences of each of these groups, piperidine, sulfonamide, alkyl carbamate in each of the molecules, right? And then I count. So for the molecules that are active, how many molecules how many times do I see, let's say, a pyrrole? How many times do I see a sulfonamide? And for the ones who are inactive, how many times do I see a sulfonamide? How many times do I see a pyrrole? And we get a plot like this, which basically tells us in terms of and I've normalized the numbers. Instead of plotting the absolute numbers, I've normalized the numbers so that we can have them choose 0 and 1. So you see the carboxylic group, relatively it occurs more often in inactive molecules, right? So often you want to see a big difference between those two lines here, those two bars, and that will be probably an indication that the certain function, right? In this case, the sulfonamide group is one of the important ones. Now I talked about scaffold earlier. Basically, a scaffold gives you it's a method used in chemoinformatics to put molecules together. So it basically is just a representation of the circle, the rings within the molecule and the linkers. We don't talk about the side atoms, right? I will show you some examples, and that helps you put molecules together. If you have that molecules that have the same ring, same ring system, exhibit similar activity. Maybe they are all active, right? Maybe they're not. So that's what you want to know. So usually what you do is you can break molecules within scaffold to see also what's the distribution of your data set. Is your data set diverse enough? If the molecules are the same scaffold, you will only have one bar. But if they have, if it's diverse enough, you generally see several scaffolds here. So basically, I, computed the scaffold, the Lebesgue Marko scaffold for all the molecules. And then I grouped them together, I computed the size. So basically here you have about, so you have to count the number of molecules that have a specific scaffold. And there is one scaffold that, there's one scaffold group that has about 5,000 molecules. And you have, because the data set is so diverse, you have 6,958 different scaffolds. That's huge. That speaks to the diversity of the data set, right? So usually you want high number here. It could be problematic sometimes. Sometimes it could actually be helpful because it will help you develop a bigger, maybe a more powerful method. So these are the scaffolds here. So you will see here there are no side atoms, no side chain atoms here, just the rings and the linkers. And then you can actually go a step further. You can decide that you don't even want to take into consideration whether a ring is aromatic or not, or whether you have heteroatoms. You can actually decide to make it so that the scaffold only have rings, carbocycles, and carbon atoms. So you replace the N by the carbon, N by the carbon, N by the carbon, and instead of phenolate, this is going to be a set of two cyclohexanes linked together, a few cyclohexanes, right? So this scaffold group has 161 compounds. So there are 161 compounds that contain this scaffold here, right? In contrast, there are only 41 that contain this scaffold. Another method to analyze or to visualize the data is by clustering. So when you cluster, you don't necessarily look at one specific scaffold. You just look at compounds that are similar, right? And there are many metrics, many ways of calculating the similarity. Here we use the Tanimoto coefficient, and we use the fingerprint. So we're using the Morgan fingerprint to basically take a molecule and turn it into a vector of length 1024 bits. And each of these bits tells you how many times a certain feature occurs in the molecule, right? So, and then you use the Tanimoto coefficient to kind of see which molecules are similar. So the molecules that are similar for each cluster has a centroid molecule. And then once you pick the centroid molecule, then you go and look at the rest of the data set and you find what molecules are similar enough. You can specify a cutoff. You can say, I want a cutoff of 0.3. So every time I get the centroid molecule, which is the head of the cluster, every molecule that has at least a similarity of 0.3, which is very low, will be part of this. So in this case, generally, you will have a small number of clusters, but you have clusters that are very large. Here, the cluster, for example, the largest cluster has almost 5,000 compounds in it, right? And there are 513 clusters. You do the same thing and you vary the cutoff. And here you have, because I increase the cutoff to 0.4, that means it's more restrictive. So the cluster will tend to be smaller, and you have more clusters. Now you have almost more than triple the number of clusters. Now, if you increase the cutoff too much, then you end up having too many clusters, right? That might be a problem. Sometimes it's good when you have molecules that look alike, even if they are not too similar, because there might be some properties that are not maybe similar to the scaffold. There might be some small properties or small nuances, small similarities that are difficult to visualize, but that actually maybe transmit a certain signal. Maybe if a carbon, if an hydroxyl group is adjacent to a carboxyl group, then it will signify or will increase the chance of the molecule to be active, for instance, right? If you're just looking at the scaffold or you're looking at molecules that are very similar, you might not see that. So now I'm going to show you 10 molecules of the largest cluster. When I take the similarity cutoff of 0.3, you will see that here they're still kind of different. They are not dissimilar, but not as similar as you might want. So they don't have the same scaffold, because here I don't group molecules based on scaffold, but just based on similarity. So here are some examples. But then when I increase the similarity cutoff to 0.7, you will see that the molecules are more similar here compared to what we have here. So there's a trade-off, right? You want to have clusters that are large enough. You don't want to have too many singletons, right? There are advantages and disadvantages of as you are increasing the similarity cutoff here, and those are described here. Now, to visualize the data set, you can also do what we call a UMAC projection. Now, I was mentioning earlier, for the Morgan fingerprint, you have over 1,000 bits. If you want to visualize the molecule in this, in the real world, you would have to use, you have to visualize the molecule in, 1,024 dimensional space, which is impossible. We cannot do that. So what the UMAP projection does is it takes such a large vector and it compacts it. It does what we call dimensionality reduction. It compacts it into a vector, into representation of a 2D representation or 3D representation. In this case, I was shooting for the 2D representation, and it tries its best to mimic or respect the actual similarity or distance, if you will, between two molecules. So the similarity between two molecules in a 1024 dimension will be almost the same in a two-dimensional space here. So that's the goal. So you will see here that the active and inactive are not, it's not easy to differentiate them, which might be a problem, or make the process more difficult. So I'm plotting different styles here. Here I'm using a different type of fingerprint, which is much smaller. It only has 167 keys, 68 keys. And with that, I get a different plus. Here you will see that they are more active compared to more active molecules compared to inactive. Here you have some clusters of active molecules, but for the most part, active and inactive occupy a fairly similar space. Other methods to assess the diversity of the set are, similarity metrics. You have the Euclidean distance, the Manhattan distance, the cosine dissimilarity, and so on and so forth. So now we come to the data splitting, right? Here I'm using we're going to use cross validation for training the data set. We're going to use cross validation, and this usually is a better technique because it allows you to train the model several times over different data sets, and it makes the model more robust. So that's the first part, right? The second part, which should take less time to explain, I guess. We have only 15 minutes. Is about the training and the validation. So here I'm gathering all the data. So I generated molecular features using Morgan and RDKit. I also have fingerprint representation with Max and Morgan, and I have my splits here, right? So what I'm going to do is build models. But before that, there's something that I want to mention here. When you're doing your splitting, it's very important that the ratio of active against inactive is consistent, right? You're going to try to do that as best as possible. Usually, you have packages that allows you to methods that will just look at the number of actives and inactive, and every time they're going to do the splits, they are going to make sure that the ratio of active versus inactive is the same for each split, right? But it's difficult when you take into consideration the molecular feature. So fortunately, we were able to mimic the same distribution. So they are more active than inactive. Usually it's the other way around. But here they are about 1.4 times more active than inactive, right, in the whole data set. Now, in each of the folds here, or the splits, right, the ratio is almost the same. It's conserved. It's conserved, right, with a few exceptions like here, right, and here. But other than that, it's fairly conserved, which is good. So in order to train the model, we're going to use a light GBM, so it's a gradient boosting model implementation. And I provided the link so that you can see what they are, and even have some tutorials here on how to implement them. Right? So, and we're going to use a hyperparameter optimization, which is a technique that looks for the best parameters. So look at the parameters as the tools that will dictate how good the model is. It's like when you're cooking, right? You will have your salt, you will have your pepper, you will have your condiment. Now, but you want to actually know what is the quantity that you want to put for each ingredient to make the perfect sauce. So basically, that's what we're doing here. And instead of going and doing what we call a grid search, so you take all the possible quantities, and then you permutate them to get a bigger set of combinations. We actually use what we call Bayesian optimization here to basically more intelligently strategically find the parameter combinations that are suitable. So with the light BGM model, I use the molecular descriptors and I trained them and I validated, and I got the best parameters. So you can usually get the best parameters, meaning the parameters that is the best models, and then you have the validation score that is 0.4. And I'm using the balanced accuracy score here, which it will be defined a bit, later, right? So now once I have that, I want to retrain the model on the whole train and validation set. Because I was training on the train set, validating on the validation set. So I want to combine the two and then train the model there and then use that model for testing. Here I'm talking about a few of the metrics that are important to compare the models. So you have the precision and the precision and the recall, as well as the file output, right? The precision will tell you of all the predictions that you made, how many were made correctly, right? How many of the positive samples were the samples that were predicted to be positive or active, active, active. And here, for the recall, it will look at all the active molecules and figure out what is the percentage of those active molecules that are actually predicted correctly. And we can use those to test how good a model is. We have what we call the confusion matrix. And the confusion matrix basically will give you an idea of how well the model did. So on the x-axis, we have the predicted label, the label that were predicted by the model. The true labels are on the y-axis. So basically, this says among the inactive molecules, right, in the test set, right, and there were about, I would say, 558 that were inactive. You predicted 219 correctly. So inactive, inactive. Inactive molecules that were predicted as inactive. So basically less than half. Now, and then you predicted 124 incorrect. You predicted 239 incorrectly. Among the active, there are about 794. 670 were predicted correctly. 124 were predicted incorrectly. Right. So, and you use that to calculate the precision score, the recall, and so on. So sometimes, depending on what you need to achieve, you might want to prioritize the false positive rate, right, over the recall, right? So maybe you have a situation where you have limited resources for testing, because usually when you predict these molecules, when you predict these outcomes, you take the molecules that are active and you go and test them again to confirm that they're active, right? You test them now experimentally. You might not have enough resources, right? What you want is maybe a model that, yes, might not find out all the active molecules, but you want to be confident that the ones that are predicted active are truly active. In that case, you will want to have a higher precision model, a model with higher precision and lower recall. In case you have enough resources and you have other predictive tools to quickly sort out molecules, right? You want to get as many active molecules as possible. You want to identify as many active molecules as possible from your input data set. In that case, you might want a higher recall. Usually there is a trade-off. If the recall is higher, the precision is going to be lower, and vice versa. So in order to really understand what the model does, right, overall, and also as you're varying the threshold, you can plot the ROC, the ROC curve, basically, which gives you an idea of how good the model is, irrespective of the threshold that you select, right? In our case here, what the author did is they took a cutoff. So, and in our trade, so they said 50% or more means that the molecule is active, and 50, lower than 50% means that it's inactive. So in our case here, we predict the probabilities, and we say if the probability of class 1 or the probability is over 0.5, and remember, it varies between 0 and 1. If it's over 0.5, it means the molecule is active. If it's less, it means the molecule is inactive. Now, in some cases, you might want to move that threshold. Maybe your model becomes better when you reduce the threshold, right? So in that case, what you want to do here, you will see you vary the threshold, and then you will see that the precision in this case, because we have more active, the precision is higher when you increase the probability threshold. So increase the probability threshold means you are very selective. The compound has to have a strong signal, a strong probability of being active for you to select it. So that means when the model is predicting a molecule as active, the likelihood for it to be active is very high. However, it also means that you will lose a lot of the active molecules. You won't see them. And you'll see here, as you are increasing, the precision is increasing, the recall is decreasing, right? So if you have only limited resources and you don't want to, have a lot of false positive, meaning molecules that are predicted as positive but are not, you want to go with a higher precision, but then you will lose in terms of the recall. So we plot these values. Generally, this is the perfect model that predicts everything correctly. For the rock AUC, the rock curve will be this black square here. So the closer the summit here of the blue line is to this point here, the better it is. And the AUC curve, the AUC, or the area under the curve, measures the space here. So it's about 0.61 and 681, which is not bad for a model. And I would like to specify here that just for the sake of training, I used 25 steps for training the molecule, because we do that iteratively, right? You do that iteratively when you're doing hyperparametric tuning. Generally, you want to go way past that. You might want to do 100 or 150. It depends. It doesn't guarantee that the model is you are going to find a much better model, but usually the chances is higher. The chances are higher for you to find a better model. And this is the prediction recall curve. So basically, you're varying the threshold, right? As I mentioned earlier, the cutoff or the probability threshold. And you want your model to be somewhere here. So the top part of the model, so the middle of the curve, you want it to be here. So for this model, it's kind of below. So when you measure the curve or the area below this line, below this curve here, you get 0.724, which is not bad. Now, in terms of feature importance, with the light GBM model, you can see what features are more important, right? So, and for this particular type of architecture, for the gradient boosting machine, you can detect the feature importance either by how many what properties is used to split the trees that you are using to the model, because this is a tree-based algorithm. For those who don't understand, there are links here to describe what the models are. Or you can decide that you can select or calculate the feature importance based on the gain. So how much gain do you get? How much does the model get by adding this feature? So this AETA has the most important feature. So if you remove that from your descriptors list, the model is going to lose its performance quite a bit. And so there are the more lucky, basically the octanol water partition, which deal with the absorption, dictate the absorption of the molecule is a very important one. So these are a bunch of topological features that are not easy to understand. So I'm just going to focus on the model of P here, and you can see that it's also here, right? So I tried different models using here the max fingerprint, using, and this is the normalized confusion matrix. I use the ECF, so the Morgan, and I also get I got the number. So here in this case, I combine the descriptors, the Morgan fingerprint, and the max fingerprint. So I have a larger dimension, right? So, and here I got the model that was slightly better. It had a better recall, but not necessarily the best precision score. So you can then compare the ROC curve here for all the models. It appears that the one with the descriptor is not too bad. It still has the highest area under the curve, so the blue one here. And when it comes to the precision recall curve, the best model is still the one with the descriptor. Again, if you train longer, things might change a little bit here. But you can see here also that having just the descriptors that are, they seem to be expressed a lot more to be more informative than just having a bunch of ones and zeros, right? Or integer values for more here. And combining a lot of those to build one model is not necessarily the best solution. And here I'm talking about the explanation. You want to make sure that you can explain your model, you can interpret it, right? Yes, I will share it. I realize we already have time, but I will definitely share it. I will provide my email address here, basically. Please send me an email because I couldn't get all your emails, right? Send me an email to this address and I will share you the link to it. Please. I'll definitely do that. It's very important that I kind of share this with you. So here I'm explaining basically in different ways how the different features contribute to the prediction. So here the one in red push the prediction, or if you want, the probability towards positive, and the blue ones push towards the negative, right? So basically it means that the model is contributing quite a lot.
Coming back, the general audience. So is our speaker here?
Oh yes, can you hear me?
Yes, I can hear you. I'm not sure whether I can make you co-moderator. I'm not sure whether I have the right to do that. So I hope Fidele is able to do this. Or maybe you are already.
Try to share my presentation.
Yes. That looks good for me. So I think we'll start with your presentation. Very briefly, to introduce you to the audience. You're working in two places in Slovenia. One is the University of Marko, and the other is University of Primorska. And you were also involved in establishing, or the latter university where you work is also involved in bioinformatics startup in Tallinn, and your work is basically the design of novel active compounds, and this is also what you're going to present right now here. So I'm looking forward to your talk. So you need to unmute. You need to unmute your. Just well, in your meeting, you should be able to unmute the microphone.
Okay, and now you should be able to hear me, I think.
Yes, I hear you now.
Yeah, okay.
But the presentation is gone now. You have to restart.
Okay. I hope we'll remedy that. Okay. Now can you hear me?
Yes, I hear you.
Okay, perfect. So my name is Marko, and I thank the organizing committee for inviting me. We met Fidele when he came to visit us, and we keep in touch ever since. So for this lecture, I envisioned a bridge between hands-on workshops and a lecture, and I will focus just on molecular docking experiments and application of molecular docking in identification of interesting sites and proteins. And the reason for this lecture is essential steps in molecular docking. Why? Because we often see the quality of molecular docking is getting worse, not better by the time. Interestingly, yes, and we can even observe this in scientific literature, where docking protocols are misinterpreted or underreported, and so on and so on. So I will just focus a bit on some of the essential steps that should be performed in molecular docking, and I hope the audience will benefit from this lecture. So, molecular docking, finding a right pose or conformation of a compound in its receptor, compound being small molecule protein, and the receptor also being protein or any system. So we would also like to make a difference between right and wrong docking poses, or maybe more favorable and less favorable docking pose. We would like to make a difference between high and not so high affinity compounds, or make suggestions about the affinity of the compounds. So predicted affinity versus experimental measurements. We would like to get some data from molecular docking and to assess if compounds are favorable or are able to bind a certain. This slide is a bit more provocation because a couple of times you can see delta G here, but we will talk about it in the future. So just a quick question for the audience. Are you familiar with molecular docking? Yes. I would assume, yes. And okay, so here is a very nice example of the two ligands in the receptor site. And the ligand on the right side has, let's say, CN functional group, and the nitro is in the location of the water on the left side, if you can see. And this is a typical, let's say, optimization case. And you can see that the compound on the right has higher ISP50, or we can see lower ISP50 of 35 nanomolar, compared to, let's say, a compound that is not derivatized in this position. And this is a typical case that we would like to use docking for, right? To identify if this modification is favorable or not. Okay, virtual screening. Again, a computational technique that is used in drug discovery and often uses molecular docking, but not necessarily. But the key is here, multiple compounds, one target. So we would like to search enormous libraries of compounds of small molecules to identify those structures which are the most likely to have potential to bind to a typical receptor, right? Here the receptor is just a molecular docking slang, but it can be actually any protein or nucleic acid or so on. So virtual screening like a funnel, and we drop many compounds and we would like to identify one that has the best potential for binding. So what about the input data? What about the software? What about the protocol, right? More often than not, you can see in scientific literature very underrepresented in vivo experiments. We did docking with Vina and obtained these hits with binding affinity of these digits. The sentence I just mentioned contains multiple errors. And okay, not even talking about the underrepresenting of the protocol, but okay, what about the data, right? Input data software protocol, we should be very familiar, right? So first thing I would like to draw your attention to is, do you know the docking method? Do you study the literature and the references of these docking methods? And where was the method employed before? So before you do any docking, check the articles mentioning this method and check some application cases, right? Do not just use the method on the first try, but really study the reference. And of course, after you use the method, reference the method that you use. Did you inspect your protein and compounds, right? Just simple inspection. What is your protein? The quality of the protein. We'll talk about more on that later. Did you inspect the compounds, or you just blindly downloaded any compounds and just use them in your protocol because they are of the correct format or etc., right? So inspect. All the input data that you use should be carefully inspected. Do you perform global or local docking, right? If you do local docking, do you have the data to support local docking? Kiran, you were able to listen to Yannick's cons that develops state-of-the-art methods in identification of binding sites, and I really recommend studying his work on binding site identification. Do you dock to the homology model? You would be surprised how many times people use homology models for docking. This is a completely different story, right? So we are confident or not in the receptor itself. How confident will be in the results of such a docking experiment? So really inspect the model. How was it created? what templates were used for the model generation. There are now also alternative methods, like machine learning supported methods, and even there you should inspect the proteins carefully. How were they generated, right? If you don't have experimental data. Now ligands. How many times did you check will your ligand interact in a covalent manner, right? If this is the case, then complete protocol adaptation should be conducted, right? Also study of the chemistry and so on. Do you know the docking parameters? Did you inspect them? What are the sampling and optimization methods employed? So always check all the parameters that are present in the docking, right? Study the parameters and inspect them. How do they influence your experiments? And actually study the protocol itself. What are the methods for sampling and optimization? And if you know these methods, you can also adapt the parameters and, of course, modify the parameters to suit your needs. If first docking is not successful, maybe the case is the wrong parameters or the wrong experimental setup, so study that. Are only the top hits relevant? So if you do docking experiments, what do you think? Are only the top hits relevant? What would you say if I ask the audience? Okay, no answer here. So of course not, right? Docking reveals structural trends and so on. So use a little more data than just top hits obtained by a docking experiment. Use techniques like clustering and so on to make sense of the results you get out of the docking experiment. What docking energy represents a good binder? Is there such a thing as a docking energy? What would you say? Again, question to the audience. Is there such a thing as docking energy? We often see, right? We often can notice, yeah, the even free binding energy of the compound with this and this obtained via docking, right? This is, of course, nonsense. Docking cannot produce free binding energy, right? It is only a docking score. And you should study what is the scoring function. And a docking score is just a docking scoring function and not producing energy, any energy output, right? Sometimes scoring functions have the units in, I don't know, kilocalories per mole or whatever, but that is not affinity, right? So be careful and use always docking score and know what is a scoring function. Does your receptor contain metal ions or cofactors? This is very, very critical, right? So metal ions, are they supported? Are they parameterized? Does your software even see the ions in reference? What about cofactors? Should they be present? Are you docking to a step that mechanistically needs a cofactor? So this should be studied in detail. What about the docking resolution? Many docking softwares produce or do samplings with various resolutions, right? So you can adapt that. Is that important? Can you miss a relevant data entry because of this parameter? Check this very carefully. What about ligand flexibility? Flexible or rigid docking. You would be surprised how many times docking experiments are performed rigid and authors do not even notice that it was done via a rigid docking experiment. If this is so, the results are maybe not relevant, or the confirmations should be prepared beforehand. Okay, how many torsions can you optimize? So this is a very popular question. The docking used for peptide docking. Can you dock peptides? Depends, right? There are some softwares that can do. Some softwares are specifically peptide docking softwares. But you should really inspect if your ligands are too flexible, are you able to sample sufficiently their conformation, right? What about the flexibility of the receptor? Should this be studied? What about your docking experiment? Should the receptor be flexible or not? Maybe you need some other conformation than the one that is found on the PDB database to really check the flexibility of the receptor. Waters in the active site or the docking receptor, are they important? Many times authors just delete the waters in the binding site, but actually maybe some waters are critical, right? And should be kept in the docking site. So please check this. Are your docking results reproducible? Depends also on the method used, right? And of course, you should perform experiments of validation and of redocking. So check with the available experimental data, check with available experimental results, do redockings, do validation, and check if you can reproduce any poses, and then repeat your experiments if you can see some trends. When you dock transition state ligands, of course, this is again, if you study your system, maybe sometimes you are interested in a transition state, so you need to modify your input ligands accordingly. Check this in the relevant literature. Docking and complex compositions, right? Know your system, right? This is very critical. Docking is very technical experiment in silico with a specific target on which a set of ligands is docked, right? So if you have a complex systems, like many compounds, typically if you study any natural compounds, there is synergy mentioned beforehand and so on. You should really know what targets are involved in this process, and you should study biochemistry in detail. You cannot just blindly dock a library on a receptor and make presumptions that are not based on additional data. Okay, did you check the geometry of the ligand and the receptor, right? Many times, crystal structure, even experimentally, have problems, have clashes. What is going on there, right? Check that. Binding energies. Are there any data, experimental binding energies that can be used for you, that can identify a ligand that can use as a reference? This is very good information. NMR calculated structures. You need to do ensemble dockings. This is also a critical experiment that you can perform very easily. From ensemble docking, very easy, we can extrapolate into multiple targets. So can you dock into multiple targets? Of course, that is called inverse docking, or even target fishing in the early days, where you have one compound and a library of receptors. This is also doable, and the receptors should be prepared carefully. Again, I'm referencing Yannick's cons, and his methods of binding site identification can really help you out here. Is there missing data? Does the receptor have missing loops? This should be checked very, very carefully. So experimental validation, pre-binding energies, this should be checked. What experiments were used? And if the data is in silico, really what in silico methods were used to calculate binding energy? Certainly not docking, right? Okay, compound preparation. Compounds, are they 3D? Are they 2D? You often just see, yeah, we found compound in smiles and used it for docking. I doubt it, right? So how were the compounds prepared? How were the conformations calculated? If it's a rigid docking, maybe freehand conformation ensembles were prepared. How were they prepared? What's up with the hydrogens on the compounds? Of course, connected to ionization. Where was that calculated? How was it calculated? Were your compounds ionized? What environment are they in? This is critical information. This is critical for successful docking experiment. Tautomery, again, connected to the previous points. Check carefully, right? Stereocenters, critical stereocenters, right? Are they present? Do you know, right, the configuration of the stereocenters? This should be checked. Structural faults, you'll be surprised how many structural faults are found in the commercial and free available libraries. And of course, pre-processing, filtering, and so on. Protein preparation, you download it as a PDV and use it for docking, right? Directly. No. What about hydrogens and ionization of the targets? Critical steps. Many times, more often than not, residues are missing. They should be modeled. What about loops? Do they engage in your active site? They should be modeled, checked if they engage in your active site. What about temperature factors? Is the structure useful for you at all, right? Maybe there are, in the crystal, there are multiple proteins, right? Select the one with the highest probability. So the highest probability of the location of the atoms, right? And the lowest temperature factors. What about structural faults? Are they present? Many times they're present. Correct this and model the rest of the protein. Check the target references. They should be checked thoroughly. Where was this protein published? Did the authors maybe comment on any problems that you see, right? Maybe authors can immediately identify, yeah, you have two chains. Chain A has very high temperature factors, and we are very content with chain B and so on. And you can use then chain B or whatever. So check the literature. Removal of buffer or any experimental media. Of course, many times you can just check all the small molecules that are present, but this is not smart, right? So remove buffer, remove any residual molecules from the experimental media. What about the waters? Will you remove them, leave them? Analysis of water networks should be done. Software for water analysis should be used. Ions, the same. Are they critical? Are they present in your active site? If so, inspect them very carefully. Maybe you don't have them in your protein, but a similar protein with better resolution has an ion, and you have a reference that says that that ion is critical for functioning of that protein, so it should be left in, right? Check this. Dummy atoms, maybe sometimes in nanomer structures and so on, are they in? Of course not, right? So you should be careful of this kind of atoms. Unknown ligands, right? Any ligands that are unknown, you should inspect them, check them, what is going on, right? Covalent bonds sometimes missing but should be there. Check them very carefully and inspect if they should be modeled. What about occupancy? Are some amino acid residues oriented in two similar places that crystallographer deems could be possible, right? Check the occupancy, calculate which orientation is better. Terminal caps sometimes present, sometimes not. Do you need them? Use this in your preparation. So this is like a typical molecular docking protocol of these steps that I talked about. So ligand setup, protein setup, ligand representation, protein representation, and then going into docking, right? Then I will touch upon one other side. This is binding site detection. You have many methods like topological or structure-based cavity detection methods like caviar, very known. Then you have machine learning-based methods, dock site free, Q site finder, loop site, and you have template or similarity-based methods that are state-of-the-art, like Provis, that you had an opportunity to listen to. And then you have various sampling-based methods like MD or MixMD. And one method like this is method based on sampling with molecular docking. So we generate a volume around the protein and we sample, like in blind docking experiment, the whole surface of the protein. And this can really help you sometimes to avoid doing blind docking experiments in the future. This is very similar to MD or mixed MD sampling. We use several probes, and for example, EGCG is a typical probe, like the molecule on the bottom left, that has many interaction points and can be used to sample where the protein can for example, make hydrogen bonds. And then the protocol is like this. You prepare protein system, calculate protein surface, you do probe selection and do molecular docking. Of course, then you check the poses and then you do clustering of the poses using usually some density-based clustering algorithm and identify where do the poses cluster. And this is a typical result. So on the left is the docking sampling result. You can see two binding sites where all the poses cluster. On the right, you can see featurizing, so various interactions are calculated. And this is then used for various dimensionality reduction methods, and then the end result is clustered to identify various clustered poses. And in this manner, we can identify binding sites that are drawn at the bottom. This is a very elegant way. So one example is DNA CAiSMD, and you can see here very effectively the active site can be identified with this simple method. This is, let's say, step 3, and the domain, again, 3 typical binding sites can be identified with this method, and of course, I also can be correlated with previous literature. And to conclude, this is a probe-dependent method, and of course, should be coupled to various other state-of-the-art methods, like PROBIS, of course, that is really supported by a large chunk of data. Here I would also stretch out with a CmDock recommendation. This is one docking software that is free and open source, and you can use it freely. And it's just one of the plethora of softwares that are available for you. And with this, I would like to say thank you for listening to me, and I will end this presentation. Thank you.
Yeah, thank you very much for your interesting insight. And I believe even though they are already, we can have questions if the audience has some. Yeah, Jonathan and Tua, and then Lucas, or Lucas, first Jonathan. You have to unmute yourself, Jonathan.
Yeah, thank you. That's a very good lecture. Briefly, can you please explain the difference between binding energy and docking store given in energy values?
Yes, of course, given in energy values, yeah. Let's say when we talk about binding or free energy of binding, this is a thermodynamics, right, context, but docking, or let's say simple docking experiment, uses a scoring function for, let's say, scoring or identifying the binding of compound, right? But that scoring function, okay, of course, depends on what kind of docking software it is, but most often than not, is just an empirical scoring function that is fitted against a limited set of protein ligand complexes that has, let's say, experimental values available, right? And so the scoring function itself can only approximate, and with this approximation, we also say that we hope it can perform out of domain and can only approximate the affinity of the compounds. So it can only assess and tell us, yes, this compound probably has a potential to bind, but this is not binding affinity by itself. So if I'm exactly correct, scoring function does not have a unit, should not have a unit, and the unit of the scoring function is just arbitrary. Often it is in kilocalories per mole. Why? Because it was fitted against, let's say, some affinity measured data. But the scoring function itself is unitless. And this should be emphasized a lot.
Thank you.
So thank you. And we have another question from Lucas Paul.
Yes, thank you so much for the presenter. So I think you mentioned a lot of very important points, which actually, from my experience, I really enjoyed the presentation, and I wish to make a follow up of the questions which you raised during your presentation. And actually, I'll keep on contacting you for further clarifications. But for the time being, you mentioned some of the literature, which actually I missed it about the binding, the literature which is talking about the binding energy, binding pocket identification. I would like for, if you don't mind, you can share the link. I wish to get the that literature, and also I want to know if the CmDock you are saying, is it available also in for the Linux? And one more thing I wanted for you to make clarification about you. You mentioned about the CmDock. So can you speak a little bit about the CmDock?
Yes, of course. So first mention is, of course, I mentioned state-of-the-art protein and binding site identification. And state-of-the-art methods usually are template-based. And this is the work of Yannick that you had a pleasure of meeting today. And I put the link to one of the softwares in the chat. This is really the best method for binding site identification as we speak today. Second question, of course, CmDock is available and you are free to check it out. It is open source. And of course, you can dock ligands to various receptors. And the third question is, many times you wish to dock a flexible ligand to a flexible target, right? How do you obtain flexible target? Usually you have many options, but usually two options are the most common. One is that you let some residues be free, rotating during the docking, or you do some sampling experiments beforehand, and you take various conformations of the protein and you dock to each one of them, right? So maybe the most common case, you do an MD, sample protein conformation, prepare various conformations of your target, and then you dock to each one of them. And this is a typical experiment that you asked about. So I hope I answered your questions.
Yeah, thank you. I believe there's another question in the chat. Is there any suggestion or techniques on finding allosteric sites as opposed to active sites of enzymes? What are your thoughts on docking ligands into allosteric sites?
Yeah, this is a very, very important question that the scientific community is working on very effectively here. Yeah, allosteric sites are important, and also there are known compounds that work via allosteric sites, and this aspect should be explored. And herein, the predominant approach for identification of allosteric sites is extensive sampling techniques via molecular probes. So the methods that I mentioned, so CmD is, let's say, state-of-the-art, the best methods for this, or sampling via docking experiments like I mentioned at the end of my presentation. So I would suggest maybe exploring these two avenues.
Okay, thank you very much. Was that the answer to your question? Didn't seem to have any more additions. So I believe I would like to thank the discussion and the people participating in the discussion and also participating in the whole workshop today. Yeah, to finish or to round up today, the first day, I would like to pass over to Fidele then again. Thank you.
Thank you very much, Jutta, for sharing the session. I am very happy to see that the exchange was really rich and very participative sessions. Rich exchange between the participants and the speakers. And today we have come to an end. It was we had some technical difficulties, and we excuse ourselves for that. And we hope tomorrow is going to be better. And tomorrow we start at 9 o'clock. I have left. I will leave the link open so that you can look through. The announcements are there. We are beginning at 9 o'clock Central European time or West African time, so that those who were having difficulty getting the links, I have all the links of the YouTube channel, that's live streaming on YouTube, and also the main session is this one. This for tomorrow and Thursday, but I also have there the breakup session for session 3 and 4, which is tomorrow, and we look forward to meeting you guys tomorrow. So of course tonight I'll send out an email to remind us again. Have a good time and stay well. See you tomorrow morning. I leave it open, please.
Bye.
Bye-bye.
Thank you, Fidele.
Goodbye. See you tomorrow. Tata. Bye.
Bye bye.